I'm Wolfgang Banzhaf. I'm the John Koza Chair in Genetic Programming at the Michigan State University in East Lansing in Michigan. The definition of artificial intelligence is problematic because as soon as you have something that previously was considered a real AI task, as soon as it's successfully performed, it's not anymore AI. It's something else. It's pattern recognition that works. It's speech recognition that works. It's not AI. The problem is that intelligence is a very, very global concept. And because of that, AI is everything we can do with our computers, computationally achieving. At the same time, it's nothing because of this issue of this broadness of the idea. Okay, I think that I'm most interested in topics that involve active devices. If you look at optimization, which is the classical evolutionary computing approach, that is, for me, a bit sort of personally boring because you're waiting for one particular answer to this problem. Whereas if you have active devices like programs, algorithms, there comes another aspect, which is the active device has to adjust its complexity to the problem at hand. And it has probably to generalize a solution. So that is more challenging than just optimization, although I know that people have to work hard to find solutions to optimization problems. I found it more interesting for me to work on these active device problems with complexity adjustment. This is a terribly difficult problem because if you think about code, packages of computer code, 10,000 lines of code or 50,000 lines of code, there are all kinds of possibilities to change that and maybe to make it correct. So it is very difficult to search these spaces. And what we have learned is that you need to, in evolutionary computing in general, you have randomness as one of the processes that generates innovation. And it is very important that you have that because that provides a way of finding novel solutions. But in code repair, the possibility to change pieces of the code is so high that you have to restrict where you can actually do random manipulations, because otherwise you would get lost in the huge search spaces. So what we have learned is that actually you can do that, and you have to do that. And if you sort of reconcile yourself with the idea that you have to restrict randomness to certain positions or to certain ways of doing it, then you can actually manipulate all kinds of structures with evolution. And in hindsight, I think, for me, it became clear that this is also the trick that nature uses in its evolutionary processes. It doesn't apply randomness arbitrarily everywhere. It has certain means to restrict the randomness, to channel the creativity of the randomness it uses into certain places. For example, if you think of a DNA strand, it's not at all nucleotides that locations that there is mutations happening, but it's at particular places where it's more, strangely enough, more promising to do that, which is a channeling of the possibilities into the more promising areas. And this is based in natural evolution on its experience. It is just more successful in certain areas to do that. And nature had enough time to find these places. We're a bit more brute force and try that everywhere first. and it doesn't work because it's just too much of a search going on then. Yeah, well, from anecdotal stuff, we played a lot with robots in genetic programming early on. That was in the 90s, and so, for example, we had these robots that would want to. I mean, this is a classical thing. Would want to navigate and avoid obstacles, and they would decide to do nothing rather than do anything, because that was what our fitness functions provided them with as information. So evolution always sort of takes shortcuts that we don't calculate in, and you have to sort of gradually improve your fitness functions to the point where it can do what you actually wanted, but weren't able to define in the first place. Okay, could work on itself in the sense that it could evolve evolvability, where the evolutionary processes can accelerate. And that's, I think, what happened in nature. There's a discussion in biology about the evolution of evolvability. And I think if we get a handle on evolvability, on the speed of evolution, and can actually improve that, then we have this kind of a hierarchical or logarithmic system where you can sort of accelerate in hierarchical steps. I think that's a very nice and important thing to do. For me, I tend to agree with this in the sense that I think as much as technology is behind deep learning, in the sense that GPUs are ideally made for the manipulations, matrix manipulations that are important in neural networks. In the same sense, computing speed-ups that we are seeing through parallel computing and so on are possible to be used in evolutionary computing. And I think we have been seeing that over 20, 30 years already, but since this is an exponential process still going on at least 10 to 20 years maybe, we're going to see much more possibilities for evolutionary computing, just like we have seen for deep learning and neural networks. You would need to have a specific framework, I think, where you put this in, so that, I mean, this is a difficult question. You would need to have to put it into a particular framework that people can relate to and can sort of work in. The point that I think is very important about this is that an interactive process where you have the computer providing suggested solutions and you as the user sort of selecting from a set of those solutions and then follow up on those, that interactive evolutionary process could be used for democratization, because the computer would do all the work, would just provide the solutions maybe you would be able to relate to as a human, and then you would then command it to look into specific directions by selecting examples or selecting directions in the solution space. I think indeed that the structural evolution of deep learning networks is one important aspect of evolutionary computing these days, where you try to take what people do in deep learning as an art, namely structuring the networks, and put behind it a mechanism that automatically searches for those architectures. I think that's one of the areas where it's promising. I also think that the GI, the anti-genetic improvement idea, has a lot of potential. GI is not necessarily bug repair, but any kind of improvement of computer code. It could be based on the fact that certain computer codes consume a lot of energy, and you want to map them, move them to mobile devices where it's not so useful to have a lot of computation consuming energy, and so you would want to reduce that. And this is another genetic improvement area. I think in the area of, in general, of code evolution, I see a lot of promise over the next decade or so. That's a good question, and one that engineers always ask. So for very simple evolutionary algorithms, proofs exist of their convergence. So in that sense, from a mathematical point of view, if you simplify enough, if you model enough, then you can prove. Normally, however, you can only work with tests. You can run multiple tests on the thing and then hope by the number of tests and sort of the diversity of tests to corner the problem such that your solution is at least safe enough for certain specifications that the engineer has to encounter. So in general, it is a process that is open-ended. You can always improve on it. It's not fixed and forever sort of proven to be the case. So proving something is, in the mathematical world, possible, but in reality, it is very difficult. So in the engineering world, I think that will be something that can be never achieved 100%. Evolution in particular has this feature by the built-in randomness that there's a certain amount of surprise in the solutions that come from it. And this inbuilt creativity is something that not many, especially not many mathematically proven methods are able to do, because it is based on the unpredictability of the random number generators. Now, they are not 100% unpredictable because they themselves come out of mathematical processes, but on the level of possible solution, scanning of possible solutions, they are still surprising. And creativity is something that I think as humans we proud ourselves in having. And so if algorithms can in some way adopt a certain degree of creativity, then we as humans can better relate to the machines that have these algorithms implemented. This is a difficult question, I think, an interesting question, because there is this balance between exploration and exploitation in evolution, where you say you let it go into the sort of surprising directions at one end, and at the other end, you want a certain solution of a particular quality or so, and you force it into that direction. It's a bit like if we breed animals, then we also have to deal with this in the sense that if we want to breed a certain feature in an animal, how much greediness do we, or how much selection pressure do we put into breeding this particular feature as opposed to generally a healthy organism? And we see, for example, in dogs, that dogs have been bred heavily over the centuries, and it comes to a point where dogs become very cancer susceptible, which means at some point the greediness of our breeding is limited by the fact that life cannot achieve any more functionality, because we have sort of focused too much on particular features of this, in this case, organism. The same thing is probably true also for algorithms. If we put selection pressure too much into certain directions, it could happen that the algorithms are just not functioning properly, or are not robust enough to generally function in the environment we have foreseen. So there's a balance here. But it really depends, and I think it depends on the environment in which we want these algorithms to work. So the environment needs to determine the degree of our greediness for a particular function.